Having learned to operate a CNC machine, creation of content to cut or carve becomes the focus. Many find the design and generation of custom content to be something of a challenge and turn to commercial software and content providers to meet their needs. This is an expensive solution based around proprietary methods and software and is completely unnecessary. Generic height mapping offers a zero-cost solution based on simple common principles that apply across software and operating systems. A little knowledge and some basic techniques using free software provide a fast, flexible, and powerful means to address CNC content generation requirements. Techniques based on height mapping exploit principles and methods hidden behind the GUI of expensive software and will adapt to meet a wide range of 3, 4, and 5-axis needs. The same basic concepts apply to bitmap, vector, or 3D mesh sources. The same height map can be applied to generate either low-relief mesh content or used directly for G-coding. Views A to D show 4 images used to shape a mesh surface. To do so, colors are processed into Z-axis location for mesh vertices or nodes. The images map height into the mesh. For this reason, they are referred to as height maps or depth maps. Views A and B show the result of instant transitions in color value. Change from light value to dark, view A creates a downward step displacement. Changes from dark to lighter value, view B creates step-up deformation. Views C and D show how color gradient creates slope or curvature. Color distribution controls slope or curve of the mesh. Only 256 values are available in the Greyscale range. Mesh displacement and image to toolpath software process grayscale using a common standard. Mid-gray is processed at the 0 position. White represents the maximum positive height value. Black represents the maximum negative height value. Actual values derived from gray levels are calculated using a specified maximum value. Height maps can manipulate or offset the 0 position. This is similar to the way CNC machine 0 point can be adjusted to suit job requirements. For example, where penetration of the surface below the 0 position is not required, black can be treated as 0. This doubles the range of available gray values in the positive direction to produce a smoother convex surface. Where surface protrusion above the 0 position is not required, white can be treated as 0. This doubles the range of available gray values in the negative direction to produce a smoother concave surface. CNC 4 board methods use a generic principle to simplify creation of height map gradients. The technique exploits shapes filled with minimum and maximum color values. A simple example is shown in the image. View A shows a base layer with a black background. A circle is filled with dark gray, defining the minimum height. In View B, the background layer is hidden. A transparent layer is created and the circle is filled with a maximum color value, in this case white. View C shows the result of applying Gaussian blur to the circle selection on the transparent layer. Blurring shapes against transparency adjusts opacity around the edges to a degree controlled by blur settings. When layers below are unhidden, content around blurred edges will be visible, creating a gradient. In View D, both layers are visible. The maximum height shape on the transparent layer overlays the minimum height base layer. The combined result is a height map gradient that will deform a mesh surface or tool path. Shaping applied by the gradient is controllable. A bitmap is used for this example, but the same principle applies in work with vectors. Editing transparency of the maximum height layer adjusts the transition and shaping effect of the gradient. For bitmaps, Bezier curve editing can be applied. Adjustment to curve shaping applies similar curvature in the height map. Vector editors may use a different process, but the principle behind the shaping adjustment is identical. The relationship between image resolution and mesh subdivision impacts surface form and quality. In the image, a height map of 800 by 800 pixels, view A is applied to deform a planar mesh measuring 100 by 100 millimeters. View B subdivision setting is 8 by 8 quads. View C uses 80 by 80 quads, and View D applies subdivision of 800 by 800 quads. For quad-based meshes, subdivision settings with 1:1 pixel to quad ratio reduce the most defined output. Generic methods transfer to any application, sharing the functions and features in video tutorials. Free solutions to create height maps from 3D, bitmap and vector sources are found in Greyscale, GIMP, and Greyscale. These are mature, cross-platform applications in current development with excellent online support. Content for 3-axis CNC applications can be quickly generated using free utilities like 3D Sage or BMD Vendor. 3D Sage is recommended. It is cross-platform, has user-controlled subdivision, triangular or quad mesh options, and places low demand on system resources. BMD Vendor is a Windows-only option. Subdivision setting is calculated automatically using height map pixel dimensions. Some find BMD Vendor easier to use. Its adjustable display makes it a useful tool for live testing. For many CNC users, a basic displacement utility can meet most needs. While GMax is Windows platform only, those with particular interest in relief modeling or wishing to work using 4 or 5 axes will benefit greatly from its use. GMax offers more advanced exploitation of height maps. With live control over shaping, layered displacement, and use of non-planar non-uniform geometry, many more options are available. Functions and features operate equally well on vectors or splines to shape tool paths for 3, 4, and 5 axis cutting.